Thank you everyone for joining us. A return to the Tech Talk series here. It's been a little while. And what better way to return than to have a really exciting external speaker. Bernard is joining us today. So for those of you who don't know, Bernard Bell, a computer scientist with an electronics background, pioneered real-time melodic movement analysis for Indian music, alongside rule-based drumming modeling. He earned a 1990 PhD in theoretical computer science and undertook projects in musicology and anthropology. Co-founding the Speech Prosody Special Interest Group, he focused on prosody and language representation. Now retired, he dedicates time to healthcare research, computational musicology, and a unique corpus of grind mill songs via the People's Archive of Rural India. So truly a polymathic genius amongst us. Very excited to have you here, Bernard. And specifically, Bernard's going to be sharing a project called the Bol Processor Project, which he'll be able to speak to much more than I can. But as someone who's very interested in generative music, very excited for the talk. So without further ado, Bernard, take it away.
Thank you very much, Campbell. Thank you very much for inviting me. I'll try to be short. So I'll get immediately into the project, which started more than 40 years ago, and it was in India. So let's go back to India in 1980, because it will explain us the roots of the methodology that I followed all these years. First, I would like to remind of my collaborators, the late Jim Arnold, Hugh Bohr and Wim van der Meer, who are in the Netherlands, Jim Kippen, who is now located in Canada, and my wife Andréine, who was implied in discussions about rhythm as a Kathak dancer. Our first interest in Indian music was on the tonality, trying to find the system of tuning used in North Indian raga. To this effect, I built a Shruti harmonium, which is a very accurate keyboard instrument in which each key can be programmed to 4 different values of frequency ratios within 1 cent accuracy. So this is me on the photograph. Oh, actually, this was me because I don't wear a tie anymore. So we started working with this instrument in India, but we quickly realized that it was not a proper method for working with musicians, because there is a difference between what musicians think they should do and the thing they do actually. So we quickly decided that we should work on the performance, analyze the musical performance. To this effect, I built a pitch extractor and a melodic movement analyzer, also able to analyze within 1 cent accuracy. So this is what we got from the analyzer. We got the pitch lines, and which we call the melogram, and we could do the statistical analysis of the tonal positions used all over a performance, which we call the tonogram. And then we could compare the tonograms and set and calculate dissimilarities between tonograms. So when we had the table of dissimilarities between 30 ragas, we did multidimensional scaling to draw a map of a classification of ragas based on tonal similarities. So these are only tonal aspects, because if you play the tapes backwards, or if you cut the tape in several parts and play them in random order, you'll get exactly the same result. So the time is not involved in this kind of study. It's only the tonality. So what about time now? These are a few of the great musicians who inspired us for the study of rhythm in Indian music. Raja Chhatrapati Singh was playing the Pakawaj just now. Afaq Hussain Khan was our main informant with respect of tabla. Birju Maharaj, he was my wife's teacher in Kathak dance. He also inspired us very much with the complexity of rhythms. So we tried to create models, computational models of rhythmic pieces, but all the time when we would tell them or play them to musicians, they would smile and say, well, this sounds nice, but it doesn't make any sense. It doesn't mean anything. It's just like imitating a foreign language. So the problem was to find the meaning of the compositions. So this was the work of Jim Kippen, who worked with Afaq Hussain Khan, and he did his PhD on the tabla of Lucknow. So to summarize his work, I would say he was working on the transmission of compositional knowledge. So this is an example, Jim is speaking.
Vīna kitatakata tirikitatak tirikitatakata tirikitata tadha ghin tadha ghin tadha ghin tadha.
So he's using semi-onomatopoeic syllables, which are named bol in Hindi and Urdu, from the verb bolna, to speak. So to express the strokes on the drum. And the Kathak dancer will also express beats of the feet on the floor and the movements using the balls. So the first question that Jim asked me is, he said, I want to type balls more quickly. So if I type dha, I don't want to type D-H-A. I want to have one single key to type dha. Same with T, R, K, T, and so on. So I had to devise a system, actually a kind of word processor on the Apple II, which I wrote in a 6502 assembly language that was terrible, that took me several months, in which he could map every key to a single ball. This is why this system was called the Bol Processor.
Dhati dhagena dhatirikr dhati dhagatina kina dhati takena dhatirikr dhati dhag.
So now
dhati dhagena dhatirikr dhati dhagena dhatirikr dhati dhagena dhatirikr dhati dhagatina kina dhati takena dhatirikr dhati dhagena.
This composition material is called qaida, which means rules, system of rules based on a theme and variations. And one thing that Jim asked me in 1981, this is quite important. He told me, well, your Bol processor is nice, but in Apple Writer, I have a very practical thing, which is called find replace. I need that find replace in the Bol processor. So I was quite worried because it was very difficult to implement. And I asked him, why do you need that? And he said, you see, I've expressions like dati, dage, which are repeated many times on the page. So I just want to type a single string and then find replace to create it, to have it in one shot. So I told him I'm going to think about it. So I thought a lot about it, but I did not find a way really. So one day I was taking a night train from Delhi to Lucknow to visit Jim. And when taking night trains, I used to go to the bookstore of the railway station to buy a book. So I wanted Agatha Christie's book or something like that. But there was no Agatha Christie available in that shop. So, but that day there was another book was there, which is named Mathematical Models in Linguistics. So what is that? So I bought the book and I spent almost the night to read it all over. And when I reached Lucknow the next morning, I went to see Jim. I showed the book. I said, I have the solution. Forget about find replace. We will implement formal grammars. So what is a formal grammar? Actually, these were formal pattern grammars, because if you see the composition here, the first line is repeated on the third line. Not exactly repeated because we have this sign indicating a homomorphism. Kuli band, that means dhati dage is replaced with tati take. So we take the closed sound. And second and fourth are also repeated. The red part is a variable part and the black parts are fixed parts. So there we go with the grammar. First, we have this S, a static symbol, and then we choose between three possible structures. We've put weights to reflect the probability of using one structure on the other. And now we have a replacement of the fixed parts, A16, A8, and so on. And then what about the variable parts? Then it comes next. Variable parts are replaced with rewrite rules in the same way. And some of the rules, like this one, for instance, it says you can replace V1 with T if it is preceded with da, and if it is not followed with tere. So it has positive and negative context. So that's fine to make it work on the Bol processor. So this is the Apple II creating a variation using that same grammar. So you see the transformation, applying the rules and the real transformation in real time. So there you go, and there you have it. So actually we had an inference engine, which is running rewrite rules and producing and analyzing musical items. So that's what we call an expert system. So when you have an expert system, you have the musician, the expert, the analyst, the machine, the computer, and the theoretical model, which here is a formal grammar. And you have interactions between all the four. That means the machine should produce music that the musician will evaluate, and the machine should also be able to analyze music produced by the musician and tell whether it's consistent or not with the grammar. So it goes both ways. Then a few years later, I had to go back to France, and I joined the laboratory of Alain Kolmarer, who is the inventor of the Prolog language. And as an exercise, he asked us to implement an inference engine for Prolog 2. I did that in less than a week using the core of BP1. Then the problem we found is that constructing grammars in this manner was a bit limited. We had some musical limitations. So we thought, okay, let us analyze data. Let us make a data-driven system. So that's what we did. We created a system in Prolog 2 named QAVAID. QAVAID means grammar in Urdu, Arabic. It also means question, answer, validated, and so on. So this machine was creating grammars from a set of examples. But in order to do correct inductive learning, it had to ask questions to the musician. So in fact, it had to infer to find the implicit knowledge that the musician is using in producing, which means practically you cannot learn a language if you have only positive examples. You must have negative examples. It is a very general mathematical statement of language, formal languages. So now this is the BP2, which we implemented on macOS in 1986. We started this, and you can see that it is producing BP2 scores, what we have seen on the screen, but from that it was able to do MIDI, to communicate with MIDI. So it has MIDI output and MIDI input. And in the same way, it was communicating with Csound, but in a more simple way, creating Csound score, Csound orchestra, Csound instrument, and then Csound would create a sound file. So BP2 has a scripting language. It made it possible to automatize everything, and it reacts in real time to input events, such as computer keyboard strokes, MIDI note controllers, and so on. So it makes it possible to have several BP2s non-stop improvising together and communicating about certain criteria, such as the tempo or telling the next musician, the next BP2, it's your turn to play your piece and so on. We could imagine, we can have a kind of living orchestra using this system. But then we had to migrate from macOS 9 to macOS 10. Fortunately, Anthony Cosa was there, and he worked a lot to do this essential step. So the macOS 10 version of BP2 works up to Mojave system. And then Anthony took the initiative to create a console version for what we call now BP3. So this is BP3, Bol Processor BP3. We have the BP console, which is compiled C, and I had to create an interface for that. So I created it in PHP and JavaScript. That was very simple to work on that. And the BP console is communicating with MIDI via MIDI files and communicating with Csound via Csound scores. And then you have commands sent by the BP3 interface. So this is the way it's working now. But now we want to develop the following things. First, to re-implement the real-time MIDI, because all the code is there, but we only need a few instructions to do that. Then maybe set up a system for real-time communication with Csound, and maybe come up with different output systems which are more recent than Csound. So have open sound control, super collider, and all this. To this effect, we welcome new participants, software designers, musicians, because actually the participation can be just punctual. If we have a person who has good knowledge, good experience of real-time MIDI programming in C, then they can take care of this part. Then a person who is familiar with conversant with Csound can take care of other parts and so on, So this is not a lot of work, but it requires expertise on different fields. The BP3 interface is very simple. It deals with data, grammars, alphabet, sound objects, and Csound instruments and tonal scales. So this recording is the beginning of a non-stop improvisation played on a Roland D50 synthesizer and using a grammar done by Srikumar Subramaniam. And the idea of the grammar is for every time you make a piece, you have 20 ideas and 32 notes. So if when you use these rules, you are decrementing the idea, the number of ideas. When you use this rule, you are decrementing the number of notes until it's over. And then here you use meta variables with rewrite rules to create patterns of repetition. So this is a very interesting example of non-stop improvisation. But how about time structures now? So we're coming to the most important part of a Bol processor is polymetric structures, with first the period notation, which is the horizontal notation. So this is a katak ti, which I can recite. Takita 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 da takita 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 da kita takita 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 da. What it does, it has a change of speed, but the periods indicate beats, and we call this a fill. And what the system will do, it will expand this expression in this way with internal speed markers. So it's exactly, the pieces are exactly the same, but the first one is more comprehensive. I would say this is synthetic sugar. as computer scientists said. We have a representation which everybody can understand. That one is more complex. Now, the polymetric structures can also be vertical, means have polyphony. This is a typical, simple, very simple phrase. And this is the way it is represented. It's represented with commas, and then you have curly brackets to include it. And this is the expansion, how it is expanded internally. Again, this is syntactic sugar because this representation is very easy to figure out. I tell you much easier than that one. Unless you've learned Western classical music, it's not so easy to explain. And parts of this polymetric model are used in other software environments, not only tidal cycles by Alex, who is here. And what I'm showing is extremely simple examples. We'll see that there are much more complex ones. Let's try Mozart musical dice game, really in the BP2. So for instance, here we have a variable T3, which gives this expression. This is the piano roll representation, and this is the sound object representation. Let's go to the grammar. This is the grammar. Now we are in BP3. The grammar is very long. Yeah, that's the definition by Mozart. But what I want to see here, the machine created buttons for every variable in the grammar. So I'm interested in T3, which we have just seen, you know. I created T3. You see the image? These are the same images we saw before. We can play it? Sure, yes. So now I want to play the entire piece. Stop. Yeah, the sound is very bad because here we are playing a MIDI file using an inbuilt MIDI player. But we have the same, those images now are full. I mean, we have images of the full piece, yeah, definitely. If we want better sound, maybe we'll try the same grammar using Csound. Let's do Csound and a produce item. Yes. There we have it. And let's play it. You see? And why in tonality it's a bit better for a simple reason that in this piece we used things like G major, C major, and so on. These are scales, specific scales. So we used we used pure intonation scales. Where are those scales? Yeah, they're here. Right. Let's look at the D major scale, for instance. This is here. The scale is represented on a circle, which represents one octave, one cycle. So you have all the notes, and you have specific positions, which are harmonic positions and Pythagorean positions. And you see the scales showing the perfect fifth and the harmonic major thirds. And you have one whole fifth in red here between E and B. Now, a very important point is that all durations and rests are expressed in terms of integer ratios, like this, like that, so that we can have an absolute symbolic time accuracy. Absolute accuracy is very key word for this system, keeping the accuracy. Let's look at a more complicated piece, which I play here. Yeah, in this piece, we have a part which is called B, and you can see on the score that we have tied notes. And those tied notes you cannot render just with a plain polymetric expressions. You have to express the ties. The ties are shown in the expression. And another point of this piece, you have undetermined rests. For instance, this rest before B represent this whole duration. So I'm too lazy to calculate that duration, so I should not indicate it. I just say put any rest that is convenient here. And another rest is before B2, before A2, you know. So the machine will calculate undetermined rests to produce a polymetric expression with minimum complexity. So this is there is a mathematical calculation to find the expression which has minimum complexity, which is most likely to occur. So these are simple notes, what we've seen now. But what about these date? These are sound objects. These are not simple notes. So let's look at sound objects. Sound object can be sequences of MIDI codes or lines of a Csound score or both currently. But we could think about time objects in more general, representing video clips or phones in speech prosody, parts of speech in speech synthesis, robot controls, and so on. So time object can be something extremely general. So time objects have certain properties, metrical properties such as duration. Can we rescale them or scale them up and down and so on? Then properties with respect of MIDI channels and Csound instruments. How can we assign them? Properties about breaking the object, covering and so on, or truncated and so on. And properties about continuity, which is a topological property here. This object should have continuity in the beginning. This is why we have this green part here. We force the continuity. In this one, we have you see this small arrow is called a pivot. So it's a full arrow, so we call it a hard pivot that indicates the location of the object on the time structure. So if you're tada pum tada, so pum will be on the pivot. And here we've set the pivot not in the beginning of the object, but somewhere here. And we never relocate it. So it has to be, always has to fall here. This object is partly circular. I mean, is repeated after the beginning, you know. So if it is da da pa 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 pa, you know, and so on. So let's see how we arrange sound objects using all these properties. We have a sequence here, and we see that we're covering D4 is covering B, and this is not allowed. For instance, so we decide to truncate the beginning of B. If you cannot truncate the beginning of B, then you can move back D4 because it has a soft pivot. And if you cannot move D4, you have another choice, is breaking the tempo. That means moving all the time streaks. So this is a fermata, in fact. And then once you have done this, for instance, for the object C, you have a continuity constraint, so you'll move it back to glue to the end of B. So Bol processor scores, as we see here, they may contain mixture of simple notes and sound objects. And this time setting algorithm is very efficient because of its small complexity. It's very fast. So that's extremely important in music. So this here is another example of improvisation, but this time with sound object A, B, C, and the sound object that we've seen here. The grammar is actually a cellular automaton in which we use a substitution grammar in which rewriting goes in parallel, not in series, and not from left to right, for instance. And we use outtime sound objects. So this is an example of a piece that's been generated. Outtime sound objects like F written here. It has no duration, like chick has no duration as well. So this is a simple example. One production, a more complex one. And now the improvisation. So in this piece, there is a relocation of sound objects, so it's not really metronomic. It doesn't sound really very metronomic because of the relocation of sound objects. It's also absolutely continuous. Now let's come to Csound. Csound accepts any number of arguments that control instruments designed for this purpose. Okay, so you can map like pitch bend instructions to Csound arguments. You see? And you can also create special controls, Csound controls, like here, Kumar created a slide control to imitate the Sarasvatī vīna here. And he created the orchestra file, which we can find here. This is a Csound orchestra file used by Kumar. I won't go in detail in this. And this is what he got. He was trying to make a complex movement using all this. So this is what we got. So don't ask me to read the title of this piece because it's really, it's beyond my ability. Now, time patterns. If Pierre Boulez had made a theory about timing, he said time can be striated, means with metronome, with regular metronome, or it can be smooth, which means there is no metronome and the beats are created by one instrument or voice. So for instance, we want to create this simple piece. So this grammar will do it using T1, T2, T3, T4, which are time patterns, which will set up the ratios of durations. And this arrangement will it will all work in 10 beats. And we have a clock. We don't have a metronome, we have a clock, 120 beats per minute, 10 beats. So that's 5 seconds total duration. So this is one way of escaping the metronomic structure, but there are other ways. So this other way is to set performance controls, tempo performance controls, which now here have this combined with velocity controls and continuous velocity changes and so on this piece. So I told him, yeah, this piece is very good, but now you can use these performance tools to create a piece which will have weaving patterns, weaving movements, just like Debussy, Lamer, and so on, So he came up with this grammar. So what did he do? So first of all, he has put serial tools like transpose -1, which means you go one semitone lower. Then retro means you play the following phrase in reverse. Rotate, you play the following phrase after rotating by 3 units. And then key expand, that means you take C4 as a center, and then you multiply by -1 all melody intervals relative to C4, means you make a mirror. But there's no tempo tool. So how can this piece be waving, you know? Actually, the secret is that he has constructed the idea of self-embedding a certain structure with 5 and 3s. So does it work? So it works. So it's very interesting to see that the polymetric model is able to generate pieces with such a complexity that you don't hear the metronome anymore, and it can make sense. But the problem is what happens when you construct a phase diagram in absolute time accuracy with very complex duration ratios that will come from this grammar. Well, if you construct the phase diagram, the exact phase diagram, it will contain billions of cells. That's a big problem. The solution to avoid this is to use time quantization. Quantization, let's take a very simple example. With no quantization, we have this piece here. And then let us say, now I want the same piece, but I don't want any time interval smaller than 200 milliseconds. And here you have 166. So make it shorter. So the machine will calculate a compression rate of 2, and it will come up with this piece. Phase diagram is smaller, as you can see, and the polymetric expression is smaller. So the good thing is that the machine will immediately write the simple polymetric expression. It will never create the complex polymetric expression. So we save memory, and we save memory in the phase diagram. But in real time, the quantization is not 200 milliseconds, is often like 10 milliseconds. And in this piece that we just heard, the compression rate was more than 1 billion. So that's quite impressive. Let us finish with music by humans. So here I wrote a script to import and interpret MusicXML scores, which is a kind of a text format representing a Western musical score. This was Oscar Peterson, and let us look at the score I imported. Oh, this is a very complex thing, but actually the score is, in fact, it is one unique polymetric structure for this piece, which is about 3 minutes long. There is one unique polymetric structure. So this we cannot read easily, but to make it easier, we can just explode it. Once you have exploded it, you have one item per measure. So like the fourth measure, we can even play it. Yeah, okay. Or we can see the expansion and so on. And when you have this, you can do even better. You can create a grammar. This is a grammar we created using those measures. So this is the grammar. In the grammar, you can recognize parts of the score. They can be read, and it's quite readable. I mean, if you take time, you can understand why the durations are like this or like that, you know. And this is the music now played by Bol Processor. Yeah, I feel sorry for Oscar Peterson because now the Bol processor was playing not his music, but the score, whatever is written in the score. But you can see it's extremely complex still. And what happens to the compression rate is 6 quintillion, and the polymetric expression would contain 741 quintillion symbols. So we see we are dealing with extremely large numbers, which Bol processor is able to handle because it's in an absolute accuracy mode, you know. But the really good news is this one. The calculation took only 12 seconds, which shows that the algorithms are extremely efficient in terms of accuracy and speed. So 12 seconds is very little to calculate so many symbols. Now, yes, we finish in the Baroque period. So this is a piece by François Couperin, which also imported from the MusicXML score. So here we have things that are a bit more complicated because we have mordants, long and short mordants, which have to be rendered in a particular way, but the machine makes it perfectly. And you have this particular thing, this comma here is a breath sign. Because of the breath sign, we have to extend a little bit this measure. Instead of 4 bits, we have 25/6. So let us listen just to this part. Yeah, these are just these four parts. So when I listened to this piece played by a harpsichord player on the radio, I was not so impressed. And actually, after the performance, the radio speaker said that this piece is not often performed by musicians because it's a bit weird. And I mean, it's not appealing so much. I was surprised because it was written 33 years before Couperin's death. So he was really a mature composer. And the instrument was certainly excellent. The player was certainly excellent. So what was wrong with the piece? The only thing that could be wrong was the tuning of his instrument. So the problem, how did Baroque composers tune their harpsichords? So the reply is here. Pierre-Yves Asselin wrote a book called Music and Temperament. He did a historical, musicological, and acoustical research on all the temperaments used in Germany, France, and Italy during the Baroque period. He described them as tuning schemes for the fixed pitch instruments. You can tune your harpsichord if you read the book. And the particular thing is that the tonal positions are not expressed as frequency ratios, but in terms of sensation of consonance dissonance. So I have implemented all these procedures in the Bol processor. These are the tuning scheme now. Here they are. I have tuning schemes which are these harmonic scales that we have already seen, but now we have these tempered scales. For instance, we see this one. Okay, let's see the figure. You see now that the positions are not always located on harmonic and Pythagorean. Positions are almost anywhere on the circles. So this is a very specific tuning. This is a Italian temperament. And here you have all the buttons and everything to build this scale using transpositions, modifying notes, creating mean tones, and so on. And here, when you create the scale, it creates that script here, which is very comprehensible. And the script corresponds, in fact, to what you will be find in the book, page 106. You'll find exactly the same method. So what we do with this. Search, I have 18 tuning schemes eligible for this Les Ombres errantes by Couperin. So which one is the best one? So for this, we need a model of quantifying consonance and dissonance in melodic, ascending, descending melodic, and harmonic intervals. So for instance, you specified that perfect fifth and harmonic major third are good ones. If you find them, you put 2 marks, 1 mark for harmonic major third. And you have the bad ones, the dissonant intervals, you put negative marks, you see? And then you match the score of the music, of the piece of music, against each tuning scheme. So there you get this. You make a weight, total weight, which is actually the similarity of between the musical work and a certain tuning scheme. And here the winner is Rameau en si bémol, which is Rameau, B flat Rameau, and you find the other ones in order. So what happens with this? Let's see. Now I'm showing this on an image. Rameau in B flat is closest. Then we have some more, which are farther. And this Rameau in B flat is this tuning done by Jean-Philippe Rameau. And this is very interesting because this matches the historical information. Rameau was close to Couperin in the same period, same place. And Rameau devised this tuning scheme for pieces with flats, you know. And this is the case. We have 2 B flats and E flats in this piece. So this was good reason to think that this is the best tuning for this piece. So let's listen to it. But now we have to pay attention to the tonality, not to the ornamentation, which is done by the machine, but the tonality, how the, yeah, listen to it. I think that you can hear the quality of the tonality. And I said that when with this tuning, this music work really sounds like Les Ombres errantes, which means the wandering shadows. I mean, because he's wandering in a tonal space, he's going one way, and then he's changing the tonality, and you think, no, this is going to miss. It's not going to work, but it does work because the tuning is correct. So remember something which I showed in the very beginning, classification of ragas. It was based on tonal similarities. So we are using the same approach of tonal similarities to classify ragas or to match a baroque musical work against the tuning systems. So we are back to the same idea and using actually the same basic principle of consonance, dissonance, and perception of intervals. Now, for the takeaway, Bol Processor is a collection of open source algorithms. First, we saw formal grammars, inference engine, symbolic time in different musical systems, Indian, Western, physical settings of physical times of sound objects, use quantization to simplify phase diagrams, importing MusicXML scores, and model tuning scheme, which we may say are microtonal, and find the optimal tuning scheme matching a musical work. This is it. And again, we welcome partners, software designers, and musicians. When I say partners, there can be participants, or if anybody comes up with a business model in mind, they can go with a business model and use part of this material and all this material. I'm open to any kind of development of this project. Thank you very much.